now let's take a look at where that's going to read with the slide transistor design. So 3.3 ohms, this scale is going to be just a little bit below half scale. If we double that to 6.6 ohms, that's going to be at about a quarter of the scale. And if we measure, say, a 10 ohm resistor, that's going to be about 20% of the scale. And I've got a very low resistance here. This piece of micron wire here to this bend is about half an ohm. So we can see a half an ohm is going to be about 80-85% of the scale here for a half an ohm. So we can see that so we're about a half an ohm, about 3, about 6, about 10. That's about what our scale is going to be on the transistor design. Okay, a couple of quick comparisons on some actual capacitors.
ご希望のボタンを押してください。領収書が必要な方はボタンを押してください。
大丈夫だよ、寝坊しても。誰かがいるか。
And the output of this amplifier is still going to move up and down. Now, we do have a voltage difference between these two amplifiers, and that's what this meter circuit is trying to read. The two extremes are if there's no capacitor sitting here, these voltages are identical, therefore the swing and the output of both these amplifiers is identical. Thus, no voltage appears across this meter reading circuit, so we don't see any deflection on the meter. The other extreme is when we have a very low VSR capacitor here, that effectively shorts the signal out. The signal doesn't move at all, so you see value, and we get a full swing here, and we adjust the trimmer to get full scale reading on the meter. Now, of course, any DSR between, the effective 0 and open circuit is going to just cause a small amount of that signal to appear at this amplifier output, thus reducing the amount of voltage difference, and thereby giving us something a little bit less than full scale readings. That's how this DSR meter works. Let's try to take a look at the subwaveforms within the circuit to kind of get a better idea of how this all together. The first circuit is the oscillator. That's actually a way clever interesting circuit. So as an emitter coupled cascade over the vibrator, and it operates a little bit like a relaxation oscillator. Let's take a look at how it works. We got it instrumented up here on the scope. So channel 1 is probing the collector of Q2. Channel 2, the light blue trace here, is probing the emitter of Q1. And on the purple trace, channel 3 is probing the emitter of Q2. So let's consider what happens at power up. So power up, the voltage at the base of Q1 is going to go to about mid-rail. Remember, all the capacitors are not charged yet, so there's no voltage across Q2. What's going to happen now is the base of Q2 comes up, because the power came up, the emitter is going to come up as well. And that's going to also drive along the emitter of Q1 because the voltage of the capacitor can't change instantaneously. That's going to keep Q1 turned off. And if Q1 is turned off, that means this collector voltage is going to be near this fly rail. That turns on Q2 very hard. In fact, it saturates Q2. You can see that on the scope plus. The collector voltage is coming down, the emitter voltage is coming up, and we see the collector and emitter voltage are very close to each other, indicating that Q2 is in saturation. So the way that happens, there's going to be a voltage across R5, therefore there's some current flowing through R5. That's going to cause the voltage on this side of C2 to drop, thereby starting to charge up C2. And we can see that happening right here. See the voltage that appears at the emitter of Q1, we can see that voltage now dropping. Now eventually that voltage drops far enough for Q1 to turn on. As soon as Q1 turns on, its collector voltage gets yanked down. When that happens, Q2 turns off. So we can see that happens right here. We get down to the point where Q1 turns on. That immediately turns off Q2. We can see its collector voltage rise up. And now we're beginning the charge cycle in the other direction. Okay, so since Q2 is turned off, there's no current coming out of its emitter. So therefore, there's nothing to keep putting charge onto this capacitor. So now resistor R7 starts discharging the voltage across C2, and that voltage here begins to drop. And we can see that happening right here. So now that emitter voltage of Q2 drops to the point where Q2 eventually turns on again. Then you get a little bit of a regenerative action. As Q2 turns on, that provides a little bit of a bump to the voltage at the emitter of Q1, causing it to turn off slightly, which causes the collector voltage to raise up, which turns it on harder, and so regeneratively resets back to that original position again as the power gets turned on, and then the process starts all over again. So it's a pretty nifty oscillator circuit, and one that you'll run across very often. So let's take a look at it. Okay, so we've got our oscillator being buffered essentially and amplified again by Q3, driving top of our bridge circuit. The bridge is driving the input of these two identical common emitter amplifiers. So let's take a look now at the effect of the output of those amplifiers with different load or in the test capacitor socket. Okay, so I've got the two probes sitting at the collectors of Q4 and Q5, the outputs of these two common emitter amplifiers. And with nothing connected to the test points, we can see that those two outputs are virtually the same, so the voltage difference between them is really essentially zero, very close to zero. Now, of course, if we take and short that test point to ground, as would be the case with a